Welcome back to lecture number 2. We would continue where we have left in our lecture 1. We have started talking about material degradation, and where we have seen that we would look at the chemical or electrochemical route of material degradation, where there could be combination of mechanical action as well as there could be combination of heat or radiation. Now, if I come to this slide, if you see this slide, here it says that the material degradation can be defined in terms of loss of performance of an engineering system. Of course, loss of performance, it can be due to material loss, due to loss of color, due to loss of aesthetics, many aspects. Now, loss of performance can be related to many other parameters, such as loss of reflectivity in optical equipment due to fungal attack. This is also degradation, and once it happens, then of course, we have to throw that. For example, camera lenses. Loss of mechanical strength of a structural component exposed to corrosive medium. This, of course, we will attack this particular situation in our next series of lectures. Wear can increase the clearance between piston ring and cylinder, hence incomplete combustion of compression gas. This is also loss of performance. Now, we would not look at wear, but of course, the part of wear will be taken along with corrosion. In case of erosion corrosion, we will take wear plus corrosion. Loss of efficiency, of course, once we have corrosion related damage, we do lose efficiency of that machine. Loss of lifetime, this is natural. Once we have a degradation in the form of corrosion, that means the loss of materials, then of course, we have to replace that particular material prior to its usual time duration. And of course, lastly, extensive control component. This adds to the cost of that particular corrosion. Now, if we come to see the reasons or phenomena that can cause material degradation, there could be anything which are available in environment, because every time any material we have to expose it to the environment for our purpose, like heat, light, short wavelength, electromagnetic radiation, radioactive emission, chemical, mechanical stress and interactions with bacteria, fungi or other life forms. So, all these factors, they will be the reasons for some way or other of material degradation. Hence, the classification of material degradation according to its basic cause is a first step in any plan to protect a specific material in a specific situation. That is what we have been talking about. Now, coming to materials and environments, interesting, if I see materials, then first thing what it comes to a material scientist is basically the material tetrahedron. And in the material tetrahedron, you will see, for example, if I draw a material tetrahedron, this is a kind of material tetrahedron we see, where structure is one side, then processing, then performance, and then properties. Now, of course, when we talk about this material tetrahedron, in the structure we can also have one more criteria, which is called composition. Now, for a particular composition, this structure, properties, performance, processing, all are interrelated. So, this is a classic material tetrahedron. Now, if I come to this particular picture, this material tetrahedron, we have made some material for performing some duties. For example, some cases we need to hold a particular load, some cases we need to have a kind of protection against corrosion, or we need to also prepare material where wear can be protected, wear can be resisted, all sort of things. Now, if I consider materials, this is coming under this. Alloying compositions, it is coming under compositions, one particular field of material tetrahedron. Microstructure, which is coming under structure again. Now, this stress is basically a kind of factor which can come under processing or performance. Okay. So, processing, sometimes we do use rolling forging. So, we need to put stress. Performance means we do need to hold some load, their stress part is coming up. Now, when this particular structure, so that means the structure is made out of this particular material, alloying composition, microstructure, stress, and with some properties which will be needed for performing some duties. Now, this particular material is exposed to the environment, and our environment is does have such things which can degrade the material. For example, if I consider this part, this section, you see we have air and gas environment where temperature is a factor. Okay, sorry for the spelling mistake. Temperature is a factor, humidity, which is nothing but H2O content, PO2, of course, oxygen concentration is there. Then of course, there could be another factor which is CO2. CO2 is also available. Now, these kind of gases and environments, they have many times have negative effect on that material performance, like atmospheric corrosion of iron objects. Now, coming to surface condition, yes, so I will come to that particular surface condition a little later. Now, coming to aqueous environment, many a times that particular material or structure is either in the soil or in the water medium or in the chemicals. So, that means that aqueous environment comes into play. And whenever we come to aqueous environment, we have temperature, we have of course, the H plus ion concentration or OH plus ion, OH minus ion concentration, that time it will be called POH. Okay. So, pH, POH, of course, dissolve oxygen content, chlorine ion. So, we have just given example of chlorine ion, there could be halides, other halides, for example, fluoride, all sort of halides, they are deadly towards the corrosion of metallic objects. Now, flow velocity, this is also coming in the form of a kind of corrosion aspects. You might have heard about cavitation. The cavitation is a serious kind of damage happens due to a change in pressure in the during operation of impellers, pumps, all those stuffs. So, their flow velocity also plays a role. For example, a pipeline, if the pipeline, for example, I am just giving an example, if a pipeline is like this, that time if water is flowing like this and that water contains suspended particles, this velocity can create lot of force on this particular section, and then gradually this particular section will get corroded. This corroded or eroded rather. Okay. Now, this is a kind of factor which also leads to material degradation. This is coming due to flow velocity. Conductivity, of course, if something is placed in water and that water contains a very little amount of conducting ions, apart from of course, a little hydrogen ion on OH ion that is present because of the dissociation of H2O, then that water, the material would corrode little less compared to the if that particular water contains little bit of iron ion or chlorine ion. There it will be a hugely corroded. Now coming to the soil, if we see the soil part, there also moisture is important factor, acidity is important factor, which is H plus ion concentration, PO2, partial pressure of oxygen, even chlorine ion content. There could be a possibility of bacterial attack on the materials. So, this surface condition, that means now I am coming to the surface condition. Surface condition means if something is exposed to the gaseous environment or air environment, and below that if it is below the soil, within the soil or in the water medium or any other chemicals, liquid chemicals. Now coming to radiation, this is also another factor which can lead to problems on the materials. So, this is a kind of a relation between materials and environments, which is not a kind of very friendly relations. They are always trying to attack the materials. Now, corrosion part. So, if you see the corrosion before, let us forget about corrosion for the time being. Let us say how do we get iron? The iron, the first generally we make it iron in blast furnace, and in the blast furnace what we do, it is basically a reduction process, and in that reduction process we reduce iron ore, which is in the form of FeO, Fe3O4 or Fe2O3. These kind 3 iron oxides are reduced by carbon. Okay? That is what we always have, iron containing containing carbon. That carbon presence, if it is below 2% or 1.8%, we call it steel, and then beyond 2% carbon, of course in weight percent, it will be called as cast iron, but this is coming from the production route, which is blast furnace. Now, there we refine, this is a reduction, and then after reduction we send it to another plant which is called steel making plant, where actually we do oxidation, because once we form iron from blast furnace, it is generally called pig iron. That pig iron contains many impurities, and those impurities are to be taken care of or removed by oxidation. That means, by oxidizing those particular impurities, we remove them from the metal, and then we get steel which contains low carbon, and then that steel is taken to a milling process, means either rolling mill or forged products will get lot of iron objects. Now, that those iron objects are exposed to environment in the form of structures, in the form of utensils, in the form of many other applications, and then we see that gradually that iron is again turning into red rust, and interestingly, the red rust is nothing but these 3 oxides, mainly these oxides Fe2O3. So, what is happening? It is basically coming from rust, and then again we are turning to rust. So, it is a natural process, we cannot stop corrosion, because this rust formation, that means when the reaction happens with air, moisture and oxygen, then the rust forms, and this process is thermodynamically a feasible process. In fact, this process we need to spend a lot of energy, because thermodynamically this is stable phase. So, in order to get iron from iron oxide, we need to spend energy, we need to reduce, we need to have a lot of other factors, but from this to this is a natural process. So, the corrosion is a natural process. So, natural process cannot be stopped, it will happen. So, what we can do? We can control it. Okay? So, when we control, what do we mean by control? We mean control, that means we can prevent corrosion, rather we can reduce corrosion to a great extent. Okay? So, that is the essence of studying corrosion. So, we have to reduce or we have to control corrosion, stopping corrosion is out of question. Now, coming to definition, there are two definitions. One is practical definition. If we see the practical definition, the tendency of a metal to revert to its natural state, which relates to, if you see the previous slide. So, we are taking iron from iron oxide. Now, we are reverting iron to iron oxide. So, the second process is natural process, the first process is energy consuming process. So, this loss of and of course, when you do that, when you have this, of course, there will be loss of mass and loss of money. So, this is a practicality in it, the tendency of a metal to revert to its native state. Native state means what? Iron oxide or iron ions, those are native states. Scientific definition, yes. When we talk about scientific definition, we have uttered this word in some cases, electrochemical degradation of metal as a result of reaction with its environment. Now, here interestingly, we are using electrochemical, we are not using chemical. Remember that whenever we talk about corrosion related, corrosion kind of degradation, corrosion is of course a degradation, wear is of course a degradation, but when we talk about corrosion, that time we must consider that the metal is reacting with its environment electrochemically. That means there is a formation of metal ions. So, metal from metallic from atom, it will go into the ions. That is the scientific definition of corrosion. Now, coming to definition of corrosion, still continue. The destructive attack on a metal by electrochemical reaction with its environment, as we have mentioned. Corrosion returns the metal to its oxidized state or combined state in chemical compounds that are similar or even identical to the materials from which the metals are extracted. So, in this particular definition, we are combining both practicality as well as the scientific part of it. The first part, which is the attack on a metal by electrochemical reaction with its environment, is the scientific part, and the second part is basically the corrosion returns the metal to its native condition. Okay. So, this actually combines both. Now, since we have started talking about electrochemical reaction, gradually we will see that we will getting into the electrochemistry. So, now let us see this aqueous corrosion of zinc in HCl, which is a dilute HCl. Now, I would go to, let us get to the aspect of zinc corrosion. Let us say we start with this particular thing, zinc corrosion in dilute HCl. Now, if we have a kind of container, and in that container if we put a bar of zinc, this is zinc, and we have HCl here, this is dilute, and once we put in zinc, you will see that there are bubbles formation on the zinc surfaces, and those bubbles are coming out, and there will be vigorous bubble formation. And if we take this particular bubble, for example, you encapsulate this particular section and then take this bubble and then finally you burn a matchstick, you will see that it gets burnt. Okay. So, now this particular gas which is coming out, this gas is nothing but H2O gas. Now, if we see the reaction is zinc plus HCl equal to zinc Cl2 plus H2, and if we balance it, this is the balanced one. Now, we wondered that where is this electrochemistry taking place. That means, we have said that electrochemical reaction must happen, because zinc it is in metallic condition, and now it is going in the form of zinc chloride, and this zinc chloride is actually zinc is dissolving in the form of zinc chloride, and zinc chloride will dissolve in that particular solution, and hydrogen gas is coming out. But if we break this particular reaction into two parts, you would definitely see that yes, there are electrochemical reactions. Now, if I look at zinc, now if we take 2 electron out of zinc, it goes to zinc plus 2 plus ions. And now, since this 2 electron is coming out from zinc atom, these 2 electrons need to be taken up because charge cannot remain unbalanced. So, now there are HCl, in that HCl you have H plus Cl minus if we dissociate HCl. So, these H plus will take up 1 electron and form H, and if we consider 2 H plus ion, so it is plus H, it is forming H2. So, 2 atomic hydrogen will combine each other and then form H2 gas. Now, if I see this reaction is nothing but anodic reaction, or we call it oxidation reaction, and this reaction we call it cathodic reaction, and or reduction reaction. Now, whenever there is anodic reaction or oxidation reaction, it talks about material degradation. So, that means zinc atom is going into solution. So, that means this zinc rod is gradually losing zinc. So, it is a degradation, and this degradation is happening because of this electrochemical reaction, because this reaction is electrochemical reaction. And these 2 electrons which have been released by zinc, they are taken up by 2 hydrogen atom and forming hydrogen gas. So, now you see in this entire reaction we have 2 electrochemical reactions taking place. One is anodic, another one is cathodic. Now, question is, these 2 electrons, how would it move to the site of cathodic reaction? Electron must flow through a conductor. So, it is flowing. So, for example, let us say this small segment, if I zoom it. So, this is the zoom part of this, and this side zinc plus ion is forming. So, the 2 electron, this is the metal side, and this is the solution side. 2 electron is released to the metal, and now here let us say hydrogen is taking up electron and forming hydrogen gas. So, this 2 electron is flowing through this conductor, and in this electrolyte, which is also called solution, we call it electrolyte, there zinc ion and there are chlorine ion, they are combining and forming zinc chloride. So, now in order to have this entire reaction, we have 4 components. What are those 4 components? One component is anodic reaction, where anodic reaction happens, we call it anode. Where cathodic reaction happens, we call it cathode. So, these are 2 components, this is second component. Then where the electron transfer is taking place, we call it conductor. And of course, there is one more component which is electrolyte. For example, if there is no electrolyte, these reactions cannot take place. So, this electrolyte is, this is third component, and this is fourth component. So, now for this particular zinc corrosion through these electrochemical reactions, we must satisfy this condition that there must be 4 parts. One part is anode, second part is cathode, these two are forming electrodes, and then third part is conductor and fourth part is electrolyte. So, this all 4 must be there. Like that, if I see the iron part, now iron corrosion, there iron of course, if it needs to corrode, it has to form ions. So, now how can it form ions? It can lose 2 electrons and then go to +2 or 2 plus, as we are putting this convention 2 plus. So, this particular ion would then react with H2O and oxygen. So, now then this will form FeOH whole 2, and if we try to write the complete reaction, then it becomes H whole 2. Now, question is, this anodic reaction is of course there. Now, where is cathodic reaction taking place? We need to know that, and for that we need to also consider one more cathodic reaction is O2 plus 2H2O plus 4E equal to 4OH minus. So, this is anode or anodic reaction. This is cathodic reaction or cathode. Electrolyte is nothing but this, moisture becomes electrolyte. This happens when a metal object, iron object is exposed to environment. This H2O becomes the electrolyte. Now, question is, this is cathodic reaction, of course, the electron where it flows, that electron flow would happen. These happens on the anode, these happens on the cathode, and electron flows through the iron object, okay, that becomes conductor, and this becomes electrolyte. Now, in the previous case also we could see that zinc itself is acting as cathode as well as anode, because the cathodic as well as anodic reactions are taking place on zinc surface. Here also the anodic surface as well as cathodic surface, iron is behaving in the same manner. If iron becomes cathode as well as anode. Now, question is, we will not be able to tell specifically this part is cathode and this part is anode, because in the beginning it will be all statistically distributed reactions. That means, cathode, well, only we can say where the cathodic reactions happens, anode where the anodic reactions happens. So, but if I try to see the formation of this, it also follows the same route, that means electrochemistry. And iron is dissolving by forming iron ion, and there is the cathodic reaction which is oxygen reduction. This oxygen is reducing, and of course, cathodic reaction is nothing but the reduction. And in case of zinc, zinc ion is forming anodic reaction, and hydrogen ion is getting reduced and forming hydrogen. Okay. So, that becomes my entire situation. For iron corrosion as well as zinc corrosion, we follow electrochemical routes. We would continue with this particular aspects, that cathode, anode, electrode as well as conductor and electrolyte. This is the essence of, or the backbone of corrosion subject. Now, before we end this lecture 2, I would like to just tell you that of course, corrosion is deadly, but some cases corrosion of course helps. Now, let us give some examples. You would be surprised to see that some of the cases, yes, the corrosion actually helps. One classic example is, let us come to this, battery. Now, in the battery we of course have corrosive reactions. Now, carbon rod which is acting as cathode, zinc casing is acting as anode, and then because zinc case is corroding, it is releasing electron, and that electron is flowing through this particular external circuit, external conductor, and that is what we are getting, a glowing light. So, the battery is designed on the basis of corrosion, because zinc is corroding, that is what we are getting electrons, and that is available for glowing lights. Now, this is another example, the microstructures, which is the bread and butter of material scientists, because these microstructures are needed to correlate property and structures. Now, another example is porous silver. There are porous gold, which are very good catalyst. They are formed by dealloying. For example, zinc silver or gold silver, if we form alloys, then specifically, and then we can take out silver in case of gold silver, or we can take out zinc in case of silver zinc alloy, and then form porous network like this. And finally, I come to this example, which is called galvanic zinc application. Galvanization is the popular method where we protect iron structures. This also is the corrosion is the basis of galvanization or galvanic zinc application. Zinc corrodes and zinc becomes my sacrificial anode, and then iron is protected, iron becomes my cathode. So, at the end, let me end this lecture by saying our aim is to understand thermodynamics and kinetics of corrosion, different forms and reasons of corrosion, and of course, finally, we would look at protection and preventive mechanisms for corrosion. Thank you very much. Let us stop today. Thank you.